sample exam 5, I think this sample is better. It's a better approximation, if you will, of what I would actually test on in this particular chapter. So I call it the updated version. Number 1, part A, you want to integrate x squared plus x plus 1 all over the square root of x dx. I'm going to break each part, break it up. So this is x squared over the square root of x plus x over the square root of x plus 1 over the square root of x dx. So this is the integral of x squared divided by the square root of x, so that's x to the, this is x to the 2 minus a half, plus this is x to the 1 minus a half, and this is plus x to the negative 1 half. So this is now the integral of x to the 3 half plus the integral of x to the 1 half plus x to the negative 1 half dx. So we get x to the 5 halves divided by 5 halves plus x to the 3 halves divided by 3 halves plus x to the 1 half divided by 1 half plus c. And so now we clean this up, and we have 2/5 times x to the 5 halves plus 2/3 times x to the 3 halves plus 2 times x to the 1 half, then plus c. Well, I can squeeze part B here. Part B, the integral of x plus 3 dx. Let's integrate that directly. This integral of x is 1/2 times x squared plus the integral of 3 dx. This is 3x, then plus c. That's all she is. Number 2, part A, you want to integrate the tangent squared x plus 1 dx. And you know that this is an identity from trig. Tan squared x plus 1 is just secant squared. Now the reason why we use that is simply we know that the integral of secant squared is tangent x. At this time we do not know the integral of tangent square x. So we integrate secant square x, and we have tangent x, and since it's indefinite, plus c. Part B, the integral of x times x squared plus 3 dx. Well, let's simplify this. This is x to the 3rd plus 3x dx. So we integrate. This is 1/4 x to the 4th plus 3/2 x squared plus c. Number 3, if they give you f prime of x is equal to 6x squared, and you have an initial condition that f of 0 is equal to -1, you want to find f of x. If you give me the derivative, I can integrate that, and when you integrate the derivative, you get the function, or the position function. So f of x is equal to this integral of f prime of x dx. Now that is stated basically by the fundamental theorem, but by all means you want to integrate this guy, and in integrating we get 6x squared raised to the third power, then divided by 3. So we get 3x to the third plus some constant, and I had better put everything in there. This is 6x to the third divided by 3 to help my lame brain out. This is 2x to the third plus c. So in other words, we get f of x is equal to 2x to the third plus c. Remember that the function itself is the position vector. The first derivative gives us the velocity, and then the second derivative would give us the acceleration. So we got f of x, which is the position function. The first derivative, the velocity, the second derivative, the acceleration. To go from the acceleration to the velocity, we integrate the acceleration, and that gives us the velocity. To go from the velocity to the so-called position vector, we integrate the velocity, and it gives us the potential, or the position vector. The potential, it is correct, and we'll talk about that more so in Calculus 3. But now you take this guy, and they give us the initial condition that f of 0 is equal to 2 times 0 to the third plus c. That's supposed to equal -1. This implies that c is equal to -1. So the answer, f of x, is equal to 2x to the third minus 1. So you can go from acceleration to velocity by integrating. You can go from velocity to the position vector or position function by integrating. You can go from the position function to the velocity by taking the derivative of f. So f prime is the velocity, f double prime. Take the derivative of the velocity, you get the second derivative, and that's acceleration. Number 4, use the properties of summation to evaluate this sum, the summation, as I goes from 1 to 10 of I plus 2 to be squared. We're going to simplify all this. We'll FOIL this out. This is the sum as I goes from 1 to 10 of I squared. And that's a 1 there. This is I squared plus 2I plus 1. Simplify this out. This is the summation as I goes from 1 to 10 of I squared plus 2 times the summation as I goes from 1 to 10 of I plus the summation of I as I goes from 1 to 10. Now we have formulas for the summation of I and the summation of I squared. You recall that the summation as I goes from 1 to n of I is equal to n times n plus 1 divided by 2. And also the summation as I goes from 1 to n of I squared also has a strict formula. And it is n times n plus 1 times 2n plus 1 all over 6. So we use this information to calculate the summation. So you got the summation of I squared. I goes from 1 to 10, looking at this part. So we use this guy right here. So that becomes 10 times 11 times 2n plus 1, that's 21, divided by 6, plus 2, I'm coming here now, times summation of I, we use this guy. So this becomes 10 times 11 divided by 2. Plus, look at this part, the summation of, that's just 1 actually. This is 1, that's a 1. So we're adding up 1 10 times, it just gives you 10. So we work this guy out. We have 2 times 5 times 11 times 3 times 7 divided by 2 times 3 plus 10 times 11, 110 plus 10. 2 cancels out, 3 cancels out. So this gives us 35 times 11 plus 120. We get 385 plus 120. That gives us 505. Number 5. Use the limit process to find the area of the function. Here's a function they give us, f of x is equal to 2x squared. You own the interval from 0 to 1. So we need a couple of things. We need delta x. Delta x is given as b minus a over n. Well, b minus a, that's 1 minus 0 all over n. So we get 1 over n. Now we need to pick the values for x to go on the partition. So we have x of I is equal to a plus I times delta x. Well, a is 0 plus I times delta x. Delta x is 1 over n. So the x values on the x-axis will be determined by I over n. And we just use what was called the right endpoint. And so we are calculating the so-called area. And we know that with integration, this is the integral from 0 to 1, 2x squared dx. But they want you to use the limit process. So this is the limit, because n goes to infinity, of the summation as I goes from 1 to n of the function 2 times x to be squared, but x is determined by I over n to be squared. If I clean that n up a little bit better. Times delta x. Delta x represents dx. Delta x is this. So that's times 1 over n. So this is equal to the limit as n goes to infinity. We can take the 2 over n to the third out front times the summation as I goes from 1 to n of I squared. Now the summation of I squared, you recall, has a formula. This is the limit as n goes to infinity. This is 2 over n to the third. The summation of I squared is n times n plus 1 times 2n plus 1 divided by 6. This is the limit as n goes to infinity of 2 over n to the third. Now if you know something about the big O, the biggest term in the numerator, you can quickly get the result. If you work it out, we have n times 2n squared plus 3n plus 1 all over 6. And this is the limit as n goes to infinity of 2 times 2n to the third plus 3n squared plus n all over 6n to the third. This is the limit as n goes to infinity of 4n to the third plus 6n squared plus 2n all over 6n to the third. And you can clearly see that the horizontal asymptote, since my degree of the numerator and my degree of my denominator are the same, then the horizontal asymptote, or the limit, is the ratio of the leading coefficients. So we get 4 over 6, and you simplify that, you get 2/3. Number 6, part A. We want to integrate from -1 to 1 of 1 minus the absolute value of x dx. We want to find this area without integrating. So if you draw this out, x and y axis, the absolute value of x is the V shape, but since it's negative here, that means it's going down, and this 1 simply means that that's your height. So you go up 1, and you come down, upside down V. You're going from -1 to 1 on the x-axis. So to calculate this guy by using geometry, you notice that this is a triangle. The base is equal to 2. Right? And the height is equal to 1. So the area of a triangle is 1/2 times the base. Here B is equal to 2. Base is equal to 2 times the height, 1. So you multiply that out. You get 1 for this particular area. Very similarly, for part B, here they give us a semicircle, the square root of 4 minus x squared dx. semicircle. This is negative 2 to 2 on the x-axis, and then on the y-axis we go up a radius of 2. So this is the area. This was the area of a top. Area of a triangle. This is the area of a semicircle. So this is pi r squared divided by 2. R is equal to 2, the radius. So this is 4 pi divided by 2, and we get 2 pi. Number 7, part A, integrate the definite integral. It's definite because I know the limits of integration. We go from 0 to 1. This is 2t minus 1 to be squared dt. So we FOIL all this out. So we have 4t squared minus 4t plus 1 dt. So we integrate, we get 4 thirds t to the third minus 4t squared divided by 2. So that's just 2t squared plus 1 evaluated from 0 to 1. We plug in t to equal to 1, so we get 4 thirds times 1 to the third minus 2 times 1 to the second plus, this is t, excuse me, plus t evaluated at 1, that's just 1. Then it's minus all the terms evaluated at 0, it's just 0. So we get 4 thirds minus 2 plus 1, that's 4 thirds minus 1, and that gives us 1/3. Part B. We have the integral from negative 2 to negative 1. This is u minus 1 over u squared du. This is the integral from negative 2 to negative 1. This is u minus u to the negative 2. So write it like that. Now we integrate. You integrate u, that's u squared all over 2, minus u to the negative 2 plus 1, that's negative 1, divided by negative 1. Evaluated from negative 2 to negative 1. So we have u squared over 2 plus 1 over u, evaluated from negative 2 to negative 1. So you plug in u to equal negative 1, so this becomes negative 1 squared all over 2 plus 1 over negative 1. Then minus brackets, evaluate everything at negative 2. This is negative 2 to be squared all over 2 plus 1 over y, well, u evaluated at negative 2 is negative 2. So we simplify all of this. This is 1/2 minus 1. This is minus brackets 4 divided by 2 is 2 minus 1/2. So we have 1/2, I'll just write it out again, minus 1 minus 2 plus 1/2. So we get 1 minus 1, that goes out, so our result, the answer, So it's negative 2. And notice that the interval was on the negative side, right? From negative 2 to negative 1. So most of this particular term in this function seems to be under the x-axis. Look at part C. We have the integral from 0 to 2 of 2 minus t times the square root of t dt. Let's distribute that square root of 2 throughout. So we have the integral from 0 to 2. This integral from 0 to 2 of 2 times the square root of t minus t times the square root of t dt. This is the integral of 2 times t to the 1/2 minus t to the 3/2. Indeed, t times the square root of t is t to the 3/2. We evaluate that from 0 to 2 dt. So this gives us 2 times t to the 3/2 minus t, it's all over 3/2, excuse me, times, or minus t to the 5/2 divided by 5/2. And so we evaluate this from 0 to 2. Let's simplify that. This is 4/3 times t to the 3/2 minus 2/5 times t to the 5/2, evaluated from 0 to 2. So we have 4/3 times 2 to the 3/2 minus 2/5 times 2 to the 5/2 and minus 0. So this is 4/3 times 2 times the square root of 2 minus 2/5 times 2 to the 2nd times the square root of 2. This is 8/3 times the square root of 2 minus 8/5 times the square root of 2. This gives us 16/15 times the square root of 2. Number 8. If you're given capital F of x is equal to the integral from 1 to x of the cubed root of t dt, and you want to find f prime, capital F prime of x, well, we use the second fundamental theorem of calculus. So f prime of x is the derivative with respect to x of the integral from 1 to x of the cubed root of t dt. So we just evaluate this integral, really the function, at the upper limit. So this is simply the cubed root of x. We're finished. And this function here, this cubed root, is in terms of how it's defined, is called the identity function for the derivative in the integral. The derivative is the inverse of the integral. So you compose them together, and all you have left is the inside function, the inside term. So nothing to do there. Number 9, part A, you have the integral of x squared times x to the 3rd plus 5 to the 4th dx. You're going to use u du substitution. So let u equal to x to the 3rd plus 5. Why is that? Because its derivative happens to be also in the integrand. So this implies that du is 3x squared dx. Now I see x squared and I see dx, but I don't see the 3. So we divide here both sides by 3. That gives us 1/3 du is equal to x squared dx. Now I calculate the integral on that. This is 1/3 times the integral. This is u to the 4th du. The 1/3 du, happens to be the x squared dx, right? And then this is u, that's raised to the 4th. There it is there. So we calculate this. This is 1/3. You integrate u to the 4th, that becomes u to the 5th all over 5. It's an indefinite integral, so it's plus c. So this is 1/15 times u to the 5th. The u is x to the 3rd plus 5. That's raised to the 5th power plus c. Part B, integrate x to the 3rd all over 1 plus x to the 4th raised to the 4th dx. Now you want u to be a term such that its derivative appears also in the integrand. So here, if u is 1 plus x to the 4th, du is 4 times x to the 3rd dx. X to the 3rd dx is there. I don't have the 4. We divide both sides by 4. So 1/4 du is equal to x to the 3rd dx. So this is equal to 1/4 times the integral of 1 over u to the 4th du. 1/4 du is 1/4 du, which is here, gives us that x cubed dx. And so then we have just basically 1 over this u to the 4th. So now we simplify this. This is 1/4 times the integral of u to the negative 4th du. We try to write all our integrands, if possible, in that form. The integral of x to the n dx is set to equal x to the n plus 1 divided by n plus 1, then plus c, and you hope that n is not equal to -1. If it is, we get the natural log, and we'll talk about that in the next chapter. So anyway, integrate here. The 1/4 times u to the negative 4 plus 1, that's -3 all over -3 plus some constant. So we get -1/12 times 1 over u to the 3rd plus c. That's just -1 all over 12 times u. U is 1 plus x to the 4th, and that's raised to the 3rd power plus c. Again, u is this guy, right? 1 plus x to the 4th, and it's raised to the 3rd power. Put it there. Then you got the -1 up top, and you have the 12 downstairs. Number 10. we have this integral from 1 to 2, and it's 1 over x squared dx, where n is equal to 4. We want to use the trapezoidal rule, the Simpson's rule, and then integrate directly. So we first need delta x. Delta x is 2 minus 1 all over 4. We get 1/4. We also need x of i's, the x values on our rectangles, the x values on our rectangles there. So we use the right-hand rule always, the right endpoints. This is a plus I times delta x. Well, a is 1 plus I times delta x, that's 1/4. So we get 1 plus I all over 4. So x naught is equal to a, which is 1, plus 0 over 4. We get 1. X of 1 is 1 plus 1/4. So that gives us 5/4. X of 2 is 1 plus 2/4. It gives us 1 1/2, or just 3/2. X of 3 is 1 plus 3/4. I'm going by this formula here, so that's 7/4. And then x of 4 is 1 plus 1, and that gives us 2. So indeed, this partition is well defined because we go from 1 to 2, right? 1 to 2. So we need that information to work parts A and B. So part A, for the trapezoidal rule, we have the integral from 1 to 2 of 1 over x squared dx, and we approximate it by b minus a over 2n. So this is 2 minus 1 over 2 times 4, and then times 1 plus 2 times f of, maybe I should put everything in there, f of x naught plus 2 of f of x of 1 plus 2 times f of x of 2 plus 2 times f of x of 3 plus x f of x of 4 . And so we simplify this. This is 1 all over 8. F of x of naught. You know, where's x of naught? X of naught here is 1. Right? So this is 1 plus 2 times f of x of 1. X of 1 is 5 over 4. So this is parentheses 1 over 5/4 to be squared. Over 5/4 to be squared plus 2 times f of x of 2. X of 2 is here. F of x of 2. So this is 1 all over 3/2 to be squared plus 2 times f of x of 3. So this is 1 over 7/4 to be squared plus f of x of n. So this is just 1 over 2 squared. Why? Because the function is defined as 1 over x squared. Now we simplify all of this again. This is 1 over 8 times the expression 1 plus. This becomes 2 over 25 over 16 plus 2 over 9 over 4 plus 2 over 49 over 16 plus 1/4. And on your calculator, you can simplify that. If you want to just do it out by hand one more time, this is 1/8 times 1 plus 32 over 25 plus 8 over 9 plus 32 over 49 plus 1/4. Now this gives you 0.50899 precisely. Now part B, now I will need some of this information to work out part B. And we can borrow something from the trapezoidal rule. Let's see if we can put our answer here, 0.50899. And let's see if we can squeeze in the result there for part B. So the Simpson Rule. So this integral from 1 to 2 of 1 over x squared dx can be approximated by Simpson Rule says that we have b minus a, this time divided by 3 times n, or 3 times 4, times f of x of 0, which will be 1. This time is 4 times f of x of 1. So we can borrow these terms here. So this is 4 times 16 over 25 plus 2 times 4 over 9 plus 4 times 16 over 49, and then plus the last term, which is just 1 over 2 to the second, 1/4. Now you work this out on your calculator, and you get 0.5004. Now part C, just calculate this integral directly. This is x to the negative 2, right? So this is x to the negative 1 divided by negative 1, evaluated from 1 to 2. This is negative 1 over x, evaluated from 1 to 2. So this is negative 1/2 minus parentheses, it's negative 1 over 1. This is negative 1/2 plus 1, and we get 1/2, which is 0.5. So you notice that the Simpson's rule is a little bit closer in its approximation to the true exact value than compared to the trapezoidal rule. Thank you.